So what did we do in the last class? Anyone can recollect?
Back back propagation.
So we started to get the idea of about back propagation. So what is back propagation?
Learning by it's from mistakes.
So learning from mistakes. So what is it does? What is the idea we discussed?
Ma'am, we'll calculate the error.
Okay.
We'll change the weights accordingly, ma'am.
We will calculate the error and change the weights accordingly. Fantastic. So how are we going to update these weights? How are we going to train? That is what we will learn. So what we will do is that we will learn today in today's class, we will learn two ways of learning. Last time we saw that every time we will compute the error and then we will come back and then we will check if the error is zero. If perfect, we'll go to move on to the next sample. If the error is not zero, there is a big number associated with it. We will go and update the weight and then check for the error again. So we spoke about the error measure. So in today's class, we will learn about two ways of learning. So there are two ways of learning broadly. One is slow way of learning and another one is fast way of learning. Before going into the actual back propagation algorithm, we will see how to learn slowly and how to learn fastly. So let us assume that we have a classifier. So you are feeding a sample to the classifier. You will get an outcome. When you feed a sample to the classifier, you will get an outcome saying which class it belongs to. So what you will do, this sample has an associated label. So you will compare this outcome with the label. If the match is perfect, what we will do, we will move on to the next sample. So here let it be sample 1, then we will go for sample 2. If the match is imperfect, what we will do, we will try to improve. We will improve the weights. So how do we improve the weights? How do we learn from our mistakes? We know a mistake has been made. By comparing, we know there is a mistake. This is not matching with this one. So now the mistake is made. So we know we need to improve from our mistakes. But how do we improve? By improving the weights. So how do we improve the weights? So let us assume we have a neural network like this. So let us assume that we have a neural network like this. So this neural network has 6 layers, 1, 2, 3, 4, 5, 6. So it has 6 layers. So every layer has 3 neurons. So for the purpose of convenience, so not all the neurons are connected to every other neuron. So it is for the simplicity, not every neuron uses the output of every other neuron from the previous layer. So otherwise uh, it takes the input from the previous layer. Here if you take, it is not taking from every neuron, it is taking only from one neuron. So here it takes only from these 2 neurons, it is not taking from all the 3 neurons. For simplicity, we have drawn like this. So now what we want to know, our objective is to learn from the mistakes. So how are we going to learn from the mistakes is that for this neuron, we are going to fix some weight. Let us fix a weight, a small random number. Let us fix that as the weight to this neuron. So what we will do, now we will give the sample here. This is, let us assume this is our classifier. This is our classifier. So for this classifier, we are giving a sample. So now it has done a mistake. So what we are going to do is that for a neuron, we are going to fix a small random number. So what will happen when the sample is coming till this point, everything will be like before. Everything will happen like before. But after this point, what will happen? So everything will change. So what will happen? It will happen like a chain reaction. So now till this point, there is no confusion. After this point, so whichever, now we have changed this weight. We have fixed it as a simple small random number. So if you look at it, this neuron is using this value. So this value will change. This neuron is using this value. So this value will change. This neuron is using this W. So this value will change. So this value will change. This value will change. This value will change. This will change because it is using this one. So this value will change. This value will change. This value will change. This value will change. So here again, this value will change. This value will change. This value will change. Because till this, everything is like before. After this, what will happen? A chain reaction will take place because this neuron is using the input from this neuron. We have changed it this way. So this output will change. This one is using the input from here. This one is using the input from here. This one is using the input from here. Similarly, this one is using the input from here. This one is using the input from here. So after this, like a chain, just like a chain reaction of changes, the output neuron starting from the weights which is modified, everything will change. So the new weight will produce a new input for the neuron that uses that input, which will change the neuron's output value. Is it clear? So it will go on like this. So now what we will do is that, so now we know that we have changed this W. So what we will do is that we will add a small change to this weight. Initially, we have set a random weight. Now what we are doing that after a mistake has happened, we are adding a small number called M to that weight. So now what will happen? Cascading of actions will happen. Similar what has happened. So now we have changed it. So now the cascading of actions will happen. This will change, this will change, this will change, this will change, this will change. So all the changes will happen in the cascading layer till the output, everything will be changing. So now we have got a new output. So because of this, we have got a, let's say this is the classifier. So now we have changed that particular weight into weight plus M. So previously we got one output. Now we are getting a new output for the same sample. For the same sample, weight is changed. Since weight is changed, we are getting a new output. So now again, what we will do, we will take the label, compare it with the label. If the error is less than the previous error, what we will do, we will retain the weights. Retain the weights and go back to the next sample. And then compute the next output. If the error is greater than the previous weights, previous error, what we will do is that we will remove the weight. We will undo the changes. What we have done, we have put W plus M, no? So we will undo the changes. We will go back to the previous weight. We'll go back to the previous weight and then add another small random number. And then compute the output again. Then again compare with the label and check whether it is to the previous, if the error is less than the previous error or not. If it is, and again the loop will continue. So what we are doing initially, we are giving a sample to a classifier. We get an outcome. We take the outcome, compare it with the label. If the outcome is same towards the label, the match is perfect. What we will do, we will go to the next sample and then compare, take the output and then compare it with the label. We will go forward. If the match is imperfect, if the label is not matching with the outcome, if the outcome is not matching with the label, what we will do, we need to learn from our mistakes. So how are we going to learn? Initially, we have fixed a small random weight to the neurons. So this I am talking to only about only one neuron. But the whole case is that we are not just acting on one neuron. We will be changing all neurons' weight. So, but for example, we are taking only one neuron. So one neuron's weight is there. What we will do, we will add a small weight called M to that weight. That weight is a random number. So now what, after adding the weight, we will send the sample again and then we'll get a new output. If the new output is matching the label, then it is perfect. We will move on to the next sample. We will retain this weight. If the new output is not matching the sample, then what we will do, we will ignore this weight and then go back to the previous weight, add another small random number to it. This time it can be K. Last time we added M, it is not working. So this time we will add another random number K and then we will check the output again by comparing it with the label. So then again we will check with the label. If it is matching, we'll go on to the next sample. For every sample, we will be doing this process iteratively. So we can continue this process of picking and nudging the weights until the results improve. So this process will be continued. Until the results improve or we have tried enough number of times. So we have tried enough number of times. Then we have to move on to the next sample. So what we will do, we will be checking until it is matching. Until this is matching, we will be performing, we will be changing the weight every time. Otherwise, we will keep a count. We have to try 10 times. We have to change the weight 10 times. We have to try the weight 20 times. We call it as epochs. So we have to try 20 times. We have to try 30 times. 30 times after changing also, it is not moving. We have to move on to the next sample. So we have to keep a criteria like that. So this is the two criteria. Either till we get the good result, or we have tried enough number of times. We have to do this, repeat this process. Is this process clear? This process is same for everything. So this is a common process, but it is a very slow way of learning. So we have to go through one sample at a time. So like that for the entire training data set. So this is for the same sample we are doing it. For the entire training data set. So sample 1, sample 2, up to sample n. For the entire training data set, we have to go one by one, and then we have to go through it again and again. So every time the idea is that we will improve little bit. So for the sample number 1, we will be changing the weight as W plus M. For sample number 2, we will be changing as W plus M was the previous weight. Now you add a little bit. So every time, little bit, we will improve from our mistakes. So that it will get trained, and for every sample, it will be working continuously. So this is a process. We need to go understand that for every sample, we are going to train. We can continue this process until the network classifies every input correctly, or we have come close enough, or else our patience is exhausted. So that is the reason it is taking much time to train. So if you look at, we will say we are training for 3 days, 4 days, because every sample it has to go through. Suppose if it has thousands of data, every data it has to take, every sample it has to take, and it has to learn from the sample, it has to compute the error, and this process has to go through. So that is the reason it is taking more time. With this technique, we would expect the network to slowly improve, but there may be some setbacks along the way. Why is that? We will understand now. Why we will slowly understand why there is a setback in it. So, and again, we are not going to do this only for one weight. So if a neural network has what to say 10,000 weights, for 10,000 weights you have to change the small number. For example, I have chosen only one weight, but for every weight you have to do this. So we have to extend this to multiple random changes to multiple random weights. So if you have enough time, so that is the reason it is much time taking. So if you have enough time and resources, the network would eventually find the value for every weight that either predicts the right answer for the every sample. So we can come close to it. But do you think this is a valid way for teaching the network? Definitely not. Because if you look at it, if the model neural networks will have millions of weights. So millions of weights, look at for every sample, if you have to nudge and pick the weights for millions of weights, this is not going to be practical. This is not realistic. So the core idea which we will understand from here is that we will train our network. We'll train our network. We'll watch the output. When it makes mistakes, adjust the weights. So this is the core idea which we will take from here. So we have to train our network, watch the output every time. So if it makes mistake, adjust the weight. If it is not making the mistake, you do perfect, go to the next sample. So for every sample and for every sample in the training data set, we have to do this process. But we will learn. So this is a slow way of learning. Is it clear? So you have to understand this concept very clearly. Then only we can go to the next concept. Is it clear?
Yes, ma'am.
Okay. So this is the algorithm which we will be following. So every sample will come. So every sample will come. So when every sample comes, we will check the output with the label. We will compare with the label. If it matches perfectly well, then we will go to the next sample from the training data set and we will pass on to the network and then compute its output and compare it. So if it is not matching, what we will do, we will change the weight. How we will change the weight? We will add a small random number to the existing weight. So in weight initialization, we have seen it already. So this W is existing already. So for that one, what we will do, we will add a small random number. So how are we adding it? Those things we will see later. But now we understand that if the weight is not, sorry, if the output is not matching, we will add a small random number to every weight, not just a single weight. So every weight we will add it. And then again, we will check for the same sample. Again, we will check the output with its label, if it is matching or not matching. If it is matching, we will go to the next sample. If it is not matching, what we will do, we will undo these weights. We will remove the added weight and add some other random number to it. So this is the process it will go through. But this is not a fast process. It is a very slow process to it. So what we will take the idea of what is the learning from here is that we have to train our network, watch the output. When it makes a mistake, we have to adjust the weights. So this is the thing which we are going to take it from here. So there is one more note we need to understand here. So what is the note is that, so when we earlier saw the neural network, we had inputs, say, and we had weights for it. And we also had a term called bias. So we have been not talking about bias here. So it is worth to note that. So here what this neural network will do is that it will consider bias also as one of the weights. So when all the weights are getting changed, bias will also get changed automatically. It will also, the neural network will consider bias also as one of the weight. So when it is changing, when for every sample, when it is changing the weights of all the neurons, bias will also get automatically adjusted along the way with other weights. So far we have been seeing the slowest way of learning. So this is the process of learning. So we are improving the weights, and how we are improving the weights, we have learned it. So this is a very slowest way of learning. So now let us understand a fastest way of learning. So what do you think is the inefficiency of the previous algorithm? Can anyone think what is the inefficiency of the previous algorithm we learned?
Time consuming.
Okay, time consuming. Why it is time consuming?
We need to go sample by sample and
Here also we are going to go sample by sample only. Can you think? It is very easy to think. So what is that previous algorithm? When it makes a mistake, we are adding a random weight. So with this point, can you think why it is inefficient?
instead of
I have
random
given
weight, we will be very specific. Add according to the laws.
fantastic. So when we are adding random weight, the problem is that we never know what we are adding. So instead of subtracting, we can add more values. We will be adding weights in the wrong direction in the previous algorithm. So instead of subtracting some value, we will be going in the wrong direction. So instead of adding, we will be subtracting. Instead of subtracting, we will be adding. So the weights, when we are adding the weights in the wrong direction again and again, we never know when we will come out of that loop. So we told here that, so after adding the weight, we will check it. If it is making the mistake, again we have to change. So again also we are making the same mistake. If you are adding a positive value, next time also you are adding the same positive value. Next time also we are adding the same positive value. So we will never come out of this loop. So, but you should be actually subtracting the value from the weight. But we are adding continuously. So that is a mistake which we are making here. So we will never know when we will come out of that weight. So the adjustments, we should never know. So, and also the other problem, as you told, we have to tune each weight and we have to evaluate for entire samples. Entire sample set, we have to evaluate this weight. For the first sample, you will evaluate with the same weight. Second sample, you will evaluate the same weight. Third sample, you will adjust. For every sample, immense number of samples, you have to evaluate with these weights. So this becomes a huge problem then. So to avoid this mistake, what we should know? Any idea? So to avoid this mistake, in beforehand, we should know whether to add or subtract. If beforehand we are knowing that we have to add value, we will add only positive values. Beforehand, by looking at the error, we know that we have to subtract. We will subtract so that it will go in the correct direction. Then our errors will get adjusted. So we need to somehow know beforehand whether we wanted to nudge the weight along the positive direction or in the negative direction. Is it clear? So that it can avoid making the mistake, so that it will not get into that loop. Is it clear?
Yes, ma'am.
So what the previous algorithm was making the mistakes, like so this is what we need to know. So this point has to be very clear. So how we will know? Now we know that beforehand itself we need to know whether we have to add the weight or subtract the weight. So how? So what can get us to this point is gradient. So anyone has any idea about gradients?
It's a
Any
calculus,
idea? Yeah.
calculus function.
Okay. So with related to this, gradient in one dimension is nothing but we call it as a derivative or a slope.
It's a minimizing function, no?
So let me get you in a very simple way. So if you look at this curve is nothing but your error. So you have drawn a error curve as your error. So this gradient is nothing but the slope at each point. So you have two weights. One is the circle weight, other one is a squared weight. So for each point of this weight, you are drawing a gradient at that particular point of the error. So this is a slope. So for this point of this weight, you have drawn this slope. So if you look at the slope, this is a positive slope. So what will happen if weight is located here? If I move this weight here, what will happen? Look at the gradient. The gradient shows the error will increase. So if you move here, what will happen? So instead of this point being here, if the point is going to be here, the error is going to be larger than this one, right? So if I move towards the right, my error is going to increase. That is shown by the positive slope. So instead, if I'm going to move this circled weight to this point, what will happen at this point? My error is going to reduce. So it is shown by the negative slope. The negative slope is showing if I move in this direction, my error is going to be reduced. So just by looking at for a current error, my weight is here, my current error is here, this point. At this point, I am drawing the slope. So just by looking at the gradient, I can get to know whether I need to move in the right direction or in the left direction. If the slope is positive, then I need to move in the left opposite direction of the slope. So here, if I move in this direction, what will happen? The error is going to increase. So I need to move in the opposite direction. If the slope is positive, I need to move in the opposite direction of the slope. So similarly here. So if you look at here, the slope is positive here. So if I move towards the left, my square weight, my weight is located. If I'm going to move towards the left, what is going to happen? The error is going to increase. So if I look at the gradient, I can understand the slope is positive. So if the slope is positive towards the left side, so I need to move towards the right side. So if you move towards the right side, what will happen? If suppose if you are moving the weight to this point, look at the error. The error is less at this point when compared to the previous error. So the error will be moved. So I'm looking at here, I'm moving my weight to this point and looking at the gradient. The gradient is negative. So my error is going to be less. So I have to move this point towards the right. Whereas this point, I have to move this point towards the left. Is it clear? This is a very important concept. Is it clear?
Yes,
So basically move towards the direction where slope is negative.
Yeah, we need to move towards the opposite direction of the gradient.
Like where the gradient should be negative.
Yeah, if the gradient towards the gradient is negative. Yeah.
Okay.
If the gradient is negative, you need to move towards that point so that actually what is the slope? It is showing the direction of your error. Whether your error is positive or negative. So we understood that we need to learn beforehand whether we need to increase or decrease the weight. So what is increasing or decreasing the weight? So if I increase my weight or decrease my weight, my whole aim is to reduce the error. That is my whole objective of the training process. So what should I do with the weight? Whether I should increase or decrease so that my error is reducing. So it is not always increasing the weight, not always decreasing the weight. Sometimes you have to increase the weight, sometimes you have to decrease the weight based on your error. So this gradient will give us the direction in which our error is getting reduced. So that slope will tell you whether error will get reduced or not. So you need to move in the opposite direction of that one. So you need to move the weight in the opposite direction.
Okay. Yes.
Is it clear?
Yes, sir.
So if you look at here, you can itself come with the knowledge. So you have the circled weight here. If you look at the gradient, the error curve is different from that of the error curve which is present here. Here the error curve is like this. So here it is like this. So here it is like this. It is opposite to that of the previous curve which we discussed. So now we keep the weights here. Look at the gradient. So if you look at here, it has a positive slope. So if I move towards the left, what will happen? Error is going to increase. If I move towards the right, error is going to decrease. But whereas here, if I move towards the right, error will increase. So for the same weight, so there is different scenarios. So if you look at the squared weight here, what will happen? So if I look at here, so the slope is positive towards the right direction. So if I move towards the right, if I increase my weight. So here, this is positive direction, right? So if I increase my weight, my error is going to get increased. So what I need to do? So I looked at the gradient. The gradient has a positive slope. So if it has a positive slope, then I need to reduce the value. So here, if I looked at the gradient has a negative slope. So the gradient has a negative slope. So I need to increase the value. So whether it has a positive, so whether it has a negative slope or whether it has a positive slope, so you need to decide it. So if it has a positive slope, I need to decrease the weight value. Here it has a negative slope, so I need to increase the weight value. Is it clear?
Yes, ma'am.
So this is what? This is the fastest way of learning. So now we know whether to increase or decrease the weight based on the error. So now it will make perfect sense to you. So we have got the output. We have compared it with the label. We have got the error. So now the error is placed. So we have to compute the gradients for the error. And then with the slope of the error, with the gradients, we can know whether to increase or decrease the weight. And then based on that, we will increase and decrease the weight. So after that, we will again compute the outcome and then compare it with the label. And then if the error is less than the previous error, what we will do, we will take the next sample and then compute it. If it not, we will ignore that weight and then go for that weight. So this is the gradient. The point about the gradient is that it will work very well in the small ranges. It will not work well in the bigger ranges. It will work well in the small ranges. So inch by inch it will move, and then we will come to the later on we will learn an algorithm in optimization. We will learn an algorithm called gradient descent. In that we will know how it will move inch by inch. There is an algorithm called gradient descent. So how the gradient is descending along the error curve, we will learn. Inch by inch it will move, and it will move towards the local minima or local maximum. So we will learn that later on. Sorry, it will move towards the local minima because our error has to be small. So it has to move towards the minima. We will learn about that one. So what can be the problem here? Any idea? Here also there can be a disadvantage. What is the disadvantage? What can be the disadvantage?
We may not know whether it is a local minima or a global minima.
No. Now we are not talking about local minima or global minima. We have to move. Of course, we need. Suppose here we have to move here. We may not know whether it is a correct place or not. So we do not know. We have to move till here or we have to move till here. So that is there. So every time we will move, and again we will compare the sample, and this sample may not be the optimum thing. So we will move here. So again we have to move. So that is the thing. Even more before than that, what is a problem? The answer is on the screen.
We have to find the error graph.
No, error graph, it is easy. We are going to compare with the label and then we are going to get it. The answer is on the screen.
How do we get this curve? Whether it is an upward curve or downward curve?
Ma'am, curve, how we will get means. So what we are doing is that we are comparing it, no, ma'am, for every weight. So this is not going to happen in a single instance. So first time we will have one weight W1. For that one, we will get error 1. then we will have error W2. Then
This
for
is
that
and
one,
this
we
is
will
a
have second
preformed
error.
set then.
Sorry, ma'am.
It is a predetermined one. We arrive at this curve with a known set of samples.
Here for known set of samples. So let's understand this clearly. So you have a training set. You have n number of samples here. So every sample you will send in. For every sample you are sending in, you are going to nudge the weights. So for every weights so you have adjusted the weight for the first time. For that you will get error number 1 for
Okay,
the
ma'am.
first set of weights. For the second set of weights, we will get error 2. So likewise, for n number of weights, so you have a circle weight, you have a square weight. So for n number of weights, for each set of weights, you are going to get one error. So this is weight W, weights for the set 1, weight, second set of weight, third set of weight. For every set of weight, you are going to get it. For you have done that iteration 10 times. Then you will plot the error. Then you will get the gradient of it.
Okay, ma'am.
And then from that you will decide. After going 10 times, you will decide it. We will understand later how we can do it much more faster. This is a low level algorithm again. What to say? This is all library routines are there for it. But for better understanding, we are learning like this.
Okay.
So yeah, what could be the disadvantage here?
The curves are not touching the axis, ma'am.
No.
And
It could touch. I can draw it like this also. If it is 0, then this is a perfect one. So, okay, one more guess. You want to make it?
any clue, ma'am?
I told the answer is on the screen. Okay. So what is the thing is that this computation of the gradient should not take much time. As you told, like we have to compute for n set of weights and then we have to compute the gradient. So for every error, we have to compute the gradient. Every point of error, we have to compute the gradient. So this calculation of this gradient should not take much time. How we calculate the gradients makes a so using this gradient shouldn't be much of an advantage, but because if it is if it is time consuming to compute, then it is no use, right? We can use the earlier algorithm of nudging the weights. So we wanted to know whether we want to add or subtract the weight before, so that only we are using gradient. But if computing gradient itself is going to take much time, then it is not of no use to us. So let us, for time being, let's assume that we have an efficient way of calculating the gradient. So we will assume that that we have a quicker way to calculate the gradient for every weight for the whole network. So we would update the weight, update all of the weights simultaneously by adding a small value to each of the weight in the direction of the individual gradients. So we will assume that one. So is it clear? So in the direction of the individual gradient, every weight will be changed. So this weight will be changed based on this one. This weight will be changed based on how it is. Because if you look at it, both the weights exist for the same network. But here it is a square. For the square, we have to move this side. For the circle, we have, sorry, I made a mistake. For the squared weight, we have to move this side. For the circle weight, we have to move this side. For the same weights in the network, we have to change both the weights in a different direction. So this is a simple error curve I have drawn, but the error curve can be anyhow. So based on the individual gradient, we have to adjust the weights. So what we will do is that we will run the sample through the network. We will measure the output, compute the gradient for each weight, then use the gradient at each weight to move that weight in the right direction or the left direction. This is what we are going to do. Is it clear?
Yes, ma'am.
So for every weight, we are going to calculate the gradient. So when a sample is given, so we will initialize the weights for the network. When the sample is given, we will initialize the weights. get the output, compare it with the label, compute the error. Then for the error, for every weight, we are going to calculate the gradient. And using the gradient, we will decide whether we need to increase the weight or decrease the weight. And then based on the gradients computed from the error, we will update the weights. And then again, we will calculate the error. So if the error is matching, we'll go to the next sample. If it is not matching with the label, then the outcome is not matching with the label, then we will calculate the gradient again for that particular error and then update the weight. This is what is going to happen. For time being, there is one more note which we need to take here. For time being, we will understand there is no activation function for now. So earlier we understood that activation functions are essential to keep our whole network from becoming nothing more than an equivalent to a single neuron. So we need to use them. So in order to avoid the network collapse, we needed to have a non-linearity in the network. So we had activation layers. So, but now what we are doing is that for a moment, we will leave this activation functions for whatever we are going to discuss hereafter. Till I say we will understand that we are ignoring the activation functions. So we are temporarily pretending there is no activation function in the neurons. So for example, if you have a neuron like this, so we have three neurons A, B, C. Let the weight here be AD. Let the weight here be BD. Let the weight here be CD. So our neurons are going to, so if you look at the output of D is going to be AD into A naught plus BD into B naught. B naught is the output of B naught is the output of D. C naught is the output of C neuron. So this is going to be the output of D. So earlier we had a nonlinear function, but now, so earlier we had a nonlinear function and an activation function here. So now we understand that there is no activation function. So our neurons will emit nothing more than the sum of the weighted inputs. This is what we will understand. But later on, we will understand with the activation functions how we are working. But because to understand the concept of back propagation properly, we are going to do this. So now let us understand overall view of back propagation. So what is our goal? Our goal is to reduce the overall error for a sample. By adjusting the network weights. So in back propagation, so this is our goal. How are we going to do it? By using the back propagation algorithm. In back propagation algorithm, there are two steps. Step number 1 is called as back propagation. So what we will do here is that we will calculate and store a number called delta. This is very important. Delta for every neuron. So this number is related to network error. So what we will do, we will compute delta for every neuron. The second step is called as the update step. So what we will do is that we will update weights with these delta. So we will have the delta values at each neuron. So using these delta values, we will update the weights of the neuron. So our goal is to reduce error for every sample. How are we going to reduce the error for every sample? By adjusting the network weight. So the process of doing this one is called as a backpropagation algorithm. The backpropagation algorithm, there are two steps. The first step is called as a backpropagation itself, where what we will do is that we will compute delta for every neuron in the network. Delta is a number. So you will compute this number. So now we are introducing a new term called delta. So far we have been dealing with error, what to say, sample, error, weights. Now we are introducing a new term. So we will calculate delta for every neuron. Delta is a number. And the second step is that using the calculated delta, we will adjust these weights. So far we have been saying we know how whether we need to increase the weight or decrease the weight. But how are we going to do that? So gradient is showing the direction to us. But now we will use these delta values to update these weights.
This delta is
Clear?
a loss function, ma'am.
Sorry, sir.
This delta is a loss function, and is it an
No,
an
it is
error?
not a loss function. Delta
Okay.
is a number. No, we
Okay.
have not come to loss function and so on. Loss function is the error function. The error we are calculating is the loss function, sir. Loss
Sure,
or
sure.
error function or score function, sorry, error score, everything has the same value. So whatever we compare with the label with the, what to say, outcome, that comparison number or what to say, the difference is called as the error or a loss. So how we compare is loss function. So loss function, as there are several types of errors. So for classification, you will have a error function. For segmentation, we will have an error function. For dice error function, binary cross entropy is we will commonly use for binary classification. So the error function computes the difference between the outcome
Predicted
and the
value and
label.
the ground
Sorry?
truth. Yeah. Between prediction and the ground truth.
Yeah, that is the outcome and the label. Prediction and the ground truth. So there are different types of ways in which you calculate the error. But this is a delta is the internal number, which is used in updating the weights.
Okay.
Usually we will, when you give the backpropagation algorithm, this delta is automatically calculated. This is not a hyperparameter. So this is calculated from the gradient. So we will understand. So in the next class, we will see how to calculate this delta for one neuron, how to extend this for the other neuron. We will do all those things. Is it clear? So
Yes, ma'am.
what we will do is that the overall plan is that we will run the sample through the network. We will get the prediction, compare it with the ground truth or the label. If the error is greater than 0, we will compute a number called delta. So far, what we have been saying, if the error is greater than 0, we will go and improve the weights. That is what we are saying. No. So now what I am saying is that I am adding a statement. So if the error is greater than 0, we compute a number called delta for every neuron and store that number. If you use these delta values on the neuron, so what we will do is that we will use these delta values on the neuron output to calculate and update the values of weights. So earlier what I told, if the error is greater than 0, we will improve the weight. That is what we will make changes in the network, I told first. And then I told what is the change, we will improve the weights. Now I am telling how we will improve the weight. We will calculate a number called delta using the neuron output and the individual neuron outputs and the delta value, we will compute the weight and update the weight. Is it clear?
Yes, ma'am.
So the final step is to update every individual weight update so that it takes only the new value. So it is updating the after calculation, we have to update the weights of the neuron so that it will take only the new value. And then we will again compute the weights. And then if it is perfectly matching, we will move on to the next sample and repeat the same process over and over again. Until then, all the predictions are perfect. Or else, until we decide to stop, we will go on with this one. Is it clear?
Yes, ma'am.
Yes, ma'am.
So if this is clear, so what we did in today's classes, so we started with the back propagation. Back propagation is learning from the mistakes. So how do we learn? We calculate the error and update the weights. And how are we going to update the weight is the back propagation algorithm. So before that we wanted to understand a slow and the fastest way of learning. So the slow way of learning is picking the weights, changing the random weight, and then testing the final output, calculating the error, and then checking whether it is matching or not. If the error is larger, we will go and change the weight again. So this is a very slow process of learning. So what we did is that we took the central idea of training our network by watching the output. So every time it makes a mistakes, we wanted to adjust the weight. So we decided the faster way of learning. So the faster way of learning is knowing when to change the weight. Because the previous algorithm had an error, not an error. The disadvantage of the previous algorithm is it can make the mistakes by changing the weights in the wrong direction continuously so that it can stuck in a continuous loop. So to avoid that problem, we wanted to know in which direction we want to change the weight. So whether we decided, so to know that before we won't use the method called gradients. So using the gradient, we can know beforehand for each weight which direction we need to update the weight, whether in the positive direction or in the negative direction. So that we understood. And then we also made an assumption that we are not going to consider activation functions for now, because for the ease of computation and learning, for now we are not, later on we will consider that one. For now, for every neuron, we are not going to have a activation function. Every neuron is going to be the sum of weighted inputs. So, and we understood our goal. The overall goal is to reduce the error for each sample by adjusting the network weights. So the back propagation has two steps. The first step is calculating the delta for every neuron. So for every neuron, once the error is computed, we are going to check the error with the, once the output is computed, we are going to compare the output with the ground truth. And if the error is greater than 0, we are going to calculate a number called delta for every neuron. And then using that neuron, we are going to compute the weight and update the weights for every neuron. So this is the back propagation step. And the update step is updating using the delta, we are going to update the weight. So this is what we will learn in the next class. Is it clear?
Yes, ma'am.
Okay. If you have any doubts, then please ask. You have to create maybe in the first or second week of May, we will have a project presentation. So before that, you have to submit your project report. Last class, we have discussed about the report format. If you have any doubts or any help needed regarding your project, please feel free to reach out to me or to my postdoc. So we are happy to help you in your project. So any doubts regarding, don't worry whether it is a simple doubt or a complex doubt, any doubts or any help if you need in a project, please let me know. You have 1 month for your project completion. So last class we have in detail, we have discussed about the report format and the presentation format. So if you have not attended last class, please go through the last class for knowing the formats. So on tomorrow, we will have a tutorial on deep learning. So please attend in the department. It is between 5 to 7 in the evening. Please be there. Yeah, thank you.
Thank you, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Srinath sir, are you there? Srinath sir?
Yes, ma'am.
Sir, last class recording நான் அட்டன் பண்ண விட்டுட்டேன். ரெக்கார்டிங் இருக்குதா சார்? Sir, am I
Yes, ma'am.
audible?
Sure,
Yes, sir.
sure.
Can you please post
Sure.
it? We'll go through.
Yes.
Thank you, sir. Thank you.